Welcome back. So we were talking about lower bounds, and we basically talked about our construction, which basically was coming up with two distributions that are different but very similar, and as a result, the underlying loss functions are also different but similar. And we basically talk about the fact that we can lower bound the risk as a function of how separated our constructed distributions are, basically this part, times the probability of failure of the best possible test. Now we're going to try to lower bound this probability of failure, and therefore as a result get basically a lower bound on the rate of convergence. Okay, so let's recall that in our construction we assume the nature chooses one of these distributions with equal probability, and also let's note that the joint distribution of these observed observations G1 through GT are basically probability measures that are defined in the same sample space. They are different, but they are defined in the same sample space. Okay. And this is something we're going to use. In particular, we note that when a specific test, let's say test tilde, is saying that the result is not equal to 1, so basically the event associated with this option is going to be the complement of the event associated with the test saying that the outcome is not equal to -1. Okay, so the idea is that any testing procedure that we can have, in particular test tilde here, maps one region of the sample space. Okay, let's call it A, to value 1. So it's a function that the outcome is basically 1 or -1. It takes a part of the sample space, map it to 1. Naturally, the other part that remains is going to be the complement of that, and it's going to get mapped to -1. Okay, so therefore the events associated with these outcomes are basically the complement of each other. All right. So with that said, we can leverage this to basically relate the probability of error to the distance between the underlying data distributions. Okay. All right. So in particular, we are interested in bounding the total probability of error, the probability of the best test making a mistake, and this was basically the probability that we make a mistake on P1 times the probability that P1 was chosen by the nature, plus the probability that we make a mistake on P-1 times the probability that P-1 was chosen by the nature. And here we assume that the nature uses, again, equal probability to make this choice. So therefore, we have this half appearing here. Okay. Next, we're going to utilize what I said earlier, that the event associated with this is going to be the complement of A, and the event associated with this choice is going to be A. And these two are naturally the complement of each other. Okay. So therefore, the probability of error, the total probability of error, can be written exactly like this. Okay. So basically, the measure of A complement according to P1t plus the measure of A according to Pt-1. Okay. Now we know that if two events are complement, the probability of one is 1 minus the probability of the other one. Okay. So we can use this idea to replace this with its equivalent 1 minus the measure of A with respect to basically the measure Pt-1. Okay. So as you can see, very easy tools are leveraged to make a progress towards lower bounding the probability of failure. All right. The next step is also quite easy. So we are minimizing some constant minus something. That is equivalent to say that I'm basically have some constant minus maximizing the same thing. Okay. So we are using that idea here. So we arrive at this step. Well, it turns out that this quantity is basically precisely a celebrated notion in information theory. So this is basically called the total variation distance between two probability measures, P1 and P minus 1. Okay, so we don't need to. So this is basically the definition of the total variation distance. There are under certain assumptions there is another equivalent definition in terms of the L1 distance, but that's not quite important for us. What is important is basically this observation that the probability of failure is depends on how similar or how different these probability measures are. Okay, so basically the more similar they are, this distance is going to be smaller. In particular, if they are identical, the distance is 0, and the probability of failure is basically half. Okay, so that's essentially the worst case. It means that we cannot say anything. But as the probability distributions become more different, the distance becomes larger. So therefore, the lower bound gets weaker and weaker. So it basically is saying that there is some possibility of making good predictions, right? Now, in our case, the total variation distance intuitively depends on the separation parameter delta, because as delta was getting small, the distributions were getting similar, and as delta was getting larger, the distributions were getting more different. Okay, so this is what we're going to therefore try to make more explicit. So we want to basically make sure that I have something here that explicitly depends on delta. Okay, so that's basically our next step. So far, therefore, putting everything together, we have established this lower bound on the risk in terms of the separation of our functions and the joint distributions. So putting everything together, the lower bound is basically the Lipschitz constant, the norm of the optimal solution times the separation parameter delta, times 1 minus the total variation distance between the joint distributions PT1 and PT minus 1. And we want to basically make progress here by making sure that there is the dependence on delta becomes explicit. Okay. To do that, we actually have to work with another notion of kind of divergence or distance between probability measures, and that's the KL divergence that we have talked about before. Okay. And the idea is something that I'm going to mention here. So intuitively, TV distance is not sometimes easy to work with, given how complicated the distributions could become. On the other hand, the KL divergence has some nice properties. In particular, it satisfies tensorization that I'm going to talk about in a moment. And we can leverage that to basically make progress. Okay. Now, therefore, we will be trying to utilize KL divergence, but we don't have KL divergence here in this equation. How can we leverage KL divergence? So that's one question. And fortunately, there are relationships between total variation distance and KL divergence. In particular, two celebrated inequalities that are typically used in this context are the Pinsker inequality or the Bertagnol-Huber inequality. And both of them provide an upper bound on the total variation distance as a function of KL divergence. And it is very good for us that these are upper bounds, because if we plug these upper bounds in equation 13, we actually are moving towards the right direction. We are getting a lower bound, another lower bound on the minimax risk. So what we'll be using, therefore, are one of these inequalities. In particular, it doesn't matter much, but we're going to use the Pinsker inequality in the next slide. Okay, so why are we using KL divergence? So the reason for that is because of the tensorization of the KL. So it basically is saying that if you have joint distributions and you are interested in the KL divergence between joint distributions, you can represent that as basically the KL divergence of conditional distributions. Okay, so more formally, let's P small ti denotes the conditional distribution of a stochastic gradient at time t given the previous stochastic gradients when sample is chosen from data distribution pi. Then the total variation, the KL divergence between the joint distribution is basically sum of the expected KL divergences between the conditional distributions. Okay. Now we're not going to use this in our construction. We are going to use a much simpler upper bound. So in particular, if we can bound each of these terms, let's say deterministically, the expected value will be basically our deterministic bound. And then we have a sum. So we sum over t of some constant becomes basically t times that constant. Okay. So we're going to work with this upper bound on the KL divergence between the joint probability distributions, the joint distribution of the observations. Okay, so and this will be something that we can very easily calculate, as we're going to talk about next. Okay, so using therefore the KL tensorization and the upper one we just talked about, as well as the Pinsker inequality, we can get this bond on the risk of solution W. Again, the bond depends on G, D, and the separation parameter delta, and 1 minus, in this case, a square root of T, the total number of observations we have, times the KL divergence between the conditional distributions of the stochastic gradients when the underlying data distribution is P1 versus where the underlying distribution is P minus 1, okay? And again, the idea is that when these distributions are identical, the KL divergence is 0, so we have a very large lower bound, and when these distributions become different or very different, then the lower bound reduces. So we're gonna, as I'm going to discuss, we're going to see that this will explicitly depend on delta. So the total lower bound will be a function of delta, and we can optimize it to get the best sort of lower bound. Okay. All right. Before that, we have to calculate what this quantity is. Okay. So again, this is saying that if I fix the source of randomness in the previous iterations, okay, what's the distribution of a stochastic gradient at time t, okay? And if you recall our construction, so we said that the stochastic gradient is basically is conditionally distributed according to a Bernoulli distribution, right? So because each time we sample z from a Bernoulli distribution, so the stochastic gradient is also distributed conditionally according to a Bernoulli distribution, okay? So that basically means that if the underlying data distribution was P1, P1t will be, again, Bernoulli in this form. So it is saying that, again, it takes 1 or minus 1 with probability 1 plus delta divided by 2, 1 minus delta divided by 2. And the other conditional distribution is taking plus 1 and minus 1 with 1 minus delta over 2 and 1 plus delta over 2. So this is what it's saying. Okay. So the conditional distributions are precisely, therefore, Bernoulli distributions, and we can calculate the KL divergence between two slightly different Bernoulli distributions quite easily. In fact, we can calculate that precisely. So it's not a difficult calculation, and you can show that it's gonna be exactly what I've written here. And this is slightly involved. So what we can do is that we can approximate that by some constant C1 times delta square. So in particular, we can use the Taylor approximation of the log to get this result. Okay. So therefore, what's the implication? Well, now we have this explicit dependence on delta. So we plug that in equation 17, and we get this lower bound on risk. So it is GD delta, the separation parameter, times 1 minus some constant times delta square root of t. Now, this bond is a function of delta. In particular, it is a is it is a concave function of delta. So if this is delta, this is bound. So there is some delta here, which is the best delta. It means that it will give us the tightest lower bound. Okay, it is a concave function. We can find this maximum quite easily by taking, let's say, the gradient setting equal to 0, right? And it turns out that the one that is achieving the tightest bound is basically by setting delta to be some constant divided by square root of t. When we make this choice, the lower bound is going to reduce to basically d times g divided by square root of t, which is basically some constant. Well, we accomplished what we are looking for. So we established a minimax a bound on the minimax risk of any solution, and the lower bound matches the performance of SGD. So what this is saying, therefore, is that for the class of functions that are convex and G Lipschitz, SGD is basically a minimax optimal algorithm. However, it should be noted that for other class of functions, SGD may not necessarily be an optimal algorithm. And this is basically what we talked about before when we talk about functions that are smooth, non-convex, but they satisfy, let's say, somewhat a stronger notion of smoothness. Okay? So in particular, under that assumption, if you recall, we discussed that the de-biased version of SGD with momentum provably achieves a faster rate compared to SGD. Okay. All right. So there you go. These are some very elegant and important tools that we can leverage to basically study fundamental limits of performance for different class of loss functions. So it is an active area of research to basically study which algorithms are optimal, which are not. And in particular, establishing lower bound is very, very important because it can help us to see whether our existing methods are optimal or not. And if they are not, perhaps we can leverage the insights that we get from establishing these lower bounds to come up with better algorithms. So that brings us to the end of our special topic on lower bounds. And in the next lecture, we're going to talk about basically some other special topics, in particular the possibility of achieving faster rates for SGD and other algorithms thanks to the power of over-parameterization of modern deep learning models. I'll see you next time.